Good morning, everybody, and thanks for attending this. As Jorge noted, we had originally planned to do this as an in-person event, but because we're all in a very unique situation, and a lot of this material lends itself to being able to be done in a webinar format, we planned and made some changes to try to do it this way. So we do encourage people to use the QA feature. That'll ask the questions so that the other members of our team could act on them. And certainly if you have a question as I'm talking, you can ask, but I can't see that screen, so I'll most likely answer them all at the end. I'm going to start off with just a couple of basic things related to TCP and the Science DMZ concepts. And a lot of what I'll talk about here will motivate some of the later talks on perf-sonar and data movement and some of the exercises that the people who have the ability to log on and use the cloud infrastructure will be able to do. These materials will be posted online as well as the recording as well for future use. So the one slide that I like to start with that motivates a lot of what we do at ESnet is that we don't treat network as infrastructure. We treat it like an instrument, just like we would for any other scientific instrument that comprises the DOE science complex. And what does this mean? This means that the network is really an essential piece of the backplane of scientific data movement. It's what connects up the storage and the instrumentation and the computation. And because of this, it makes it a very critical piece of the entire mechanism. And when something becomes a critical piece of a very large project, whether it be the LHC or a fusion reactor or a big computational facility, it needs to be treated as a very critical piece. And that means that we need to monitor it, we need to understand it, we need to be able to build a lot of the infrastructure, the applications that live on top of this network so that they can be reliable and performant. And often there's some cross-cutting concerns that we need to worry about as we try to do these things. And we like to say that connectivity is really the first step in this. Making sure that it works and making sure that it all plugs in is important. But usability is really the second thing that must follow after that. A lot of people may be familiar with the Science DMZ model, and this little talk right here is meant to motivate these couple of areas that really make up this model. And this is not a new thing or a unique thing. Really, it's just using a lot of existing technologies and capabilities and approaches to make sure that we can define this backplane for science in a sane manner that will allow us to do the most that we can with this resource so that we can do scientific innovation. And what are these pieces? First and foremost, we need a friction-free network path. And we define this to mean we need highly capable network devices that are within the path. We want things to be working at wire speed. We don't want there to be any speed bumps or impediments that would prevent us from being able to do these things. And to do that appropriately, that means that we need to have deep queues, we need to have appropriate security policies that are put in place for the specifics of the scientific workflow and not necessarily the specifics of the enterprise networks that are carrying all the other traffic. If we want to have the ability to bypass certain pieces of our infrastructure, having a virtual circuit option is desirable, but it's not required. And we also want this to be located as close to, if not at, the site perimeter, because what that does is that it offloads a lot of this very important and usually very large pieces of network traffic, and it gets it away from all the other stuff. And that does two things. Number one, it ensures that our critical science flows are not impacted by all of the other enterprise use cases like IP phones and HVAC and printers and things like that. But also those things are not impacted by the larger science flows that are going to be coming in. So by segregating off these two different use cases, we're often able to do better by both of them. For the active data movement, we need to have dedicated machines. And we have termed these data transfer nodes. We'll go into a little bit of detail about this later on, but for the most part, it is a dedicated piece of hardware. It's not doing other things. It has the operating system, and it has the libraries and the applications that are all put in place just for the act of data transfer. It does not have a web browser or an email client, and it's not doing all the things that a general purpose machine would do. And there's a very specific reason for this, because we can tune the security policy and the enforcement of the scientific use case, these tools, to that. And then we don't need to worry about protecting about all of those other things because, hey, it's not running all of those other things. So this separation of authority and permissions is very powerful. It allows us to limit the degrees of movement that a given machine will have, such that we could target those policies and make sure that it's working as well as it possibly could for the active data movement, versus having to have a whole bunch of things in place to protect against the unknown. The last hardware-based piece that we need to have in here is the perf sonar measurement and testing, which we'll hear a lot about later on. This helps us ensure that paths are working okay and that we can get a good bead on how well things are performing over time. And then lastly, the piece that's often missed in this entire puzzle is engagement with the end users, talking to them to understand how they interact with the network. We as IT people often do a disservice to our scientific communities by just saying, okay, here's a thing, go out and be productive with it, instead of trying to understand what they're doing, why they're doing it, how they're doing it, and then improving upon those requirements versus building something brand new that may not even come close to meeting these needs. Talking with the scientific users to understand their applications and their use cases is just as important as building all of the different pieces underneath them. More simply put, I think we can summarize all of this into a single picture. If we design something the way that we think it should work, the users may not see this as the most appropriate way to do the things that they want to do. All of this is built for a very specific reason. We're trying to overcome some of the challenges of the major protocol that a lot of us use on the internet today, which is TCP. And what is TCP? It is really the most widely distributed and used protocol. We've termed it the fragile workhorse because it really is out there to do a very, very important job of making sure that we can communicate across vast distances. From an applications perspective, the interface really is just a set of sockets, and that makes it very easy to develop applications on top of this. And it does allow us to have this complete and lossless communication pattern. But what happens when we rely on this protocol is that because it has a lot of protections built in place to prevent congestion, collapse, and all the bad things that may happen to it, anytime that we experience a loss of some of the signal that is going to be sent on an end-to-end basis, that's going to cause TCP to react in a very specific way. It's going to back off its performance characteristics because it thinks that it is causing congestion on the network, which is bad for everybody. So because it backs off its behavior, as we may experience problems, whether it be related to an actual packet loss event due to a failing optic or something like that, or due to congestion just because of use, this is going to be the performance killer that impacts a lot of those scientific applications. And like it or not, it is a very widely used protocol, which means that if we are to get the most out of its performance, we need to be careful about how it's implemented and the networks that it runs across. So when I say packet and data loss, do note that this is a reliable protocol. We're not losing anything in this entire mechanism as we're talking about doing this. The data isn't lost forever, but it will be dropped somewhere. And this is the challenge. It's dropped somewhere along the path, and we don't exactly know where it's going to be. It's not the job of the protocol to tell us this either. If we have telemetry available from the network, we're able to make guesses about where this may happen. We're able to look at queues. We're able to run an active test, like some of the things that we'll do with perf sonar in a little bit. But we're making best guesses about how something is going to be performing and trying to engineer the paths to be as reliable and robust as possible. Typically what this means is that if something along the path is going to drop it, it's most likely because there's a device that doesn't have enough buffer space to accept it. And when something doesn't have enough buffer space to accept it, it will just drop that packet. The protocol has the mechanism to figure out on an end-to-end basis that it doesn't have all the information that it requires, and there'll be mitigations put in place to resend and compensate for that loss. This typically works out okay without a huge performance hit, but the problem that we run into is that if you drop several in a row or many over time, this is going to reduce the performance footprint and make it very hard to do these sort of things that allow you to do high performance use cases on the network. And as I said, TCP will reliably and transparently recover from all of this. Doesn't matter the tool, web, email, grid, FTP, whatever the case may be. We just don't understand what's going on at the user level. And that's why we have to rely on some of these other tools like Persona to figure this out. The best way to engineer this, of course, is to build your network big enough and be cohesive enough that you can figure out if there is one of these problems going on and prevent it before it happens. But in the case that you can't do that, you do need to have good strategies in place to mitigate, find, and fix these different things. So what does this really look like in practice? This is a graph that shows us situations of data transfer across a wide area network. So the way that you read this graph is on the left-hand column there. That's our throughput expectation. At the very top, it's around a 10 gig performance. At the very bottom, it's less than 1 gig, all the way down to nothing. And we're looking at 4 distinct plots here. The bottom axis describes the round trip time in milliseconds. So let's look first at the purple line, which is the measured no loss scenario. If I was transferring to something within the data center, within the same rack, I'm going to have a very, very small RTT, which basically means that the milliseconds are going to be anywhere from 0 to 2 milliseconds between different hosts. If these hosts are connected at 10 gigabits per second and they don't have to go across a very large network and we have a very, very small RTT, my expectation of performance is very high. I should be able to get close to 10 gig per second. I may not get all the way there due to protocol overheads and such, but for the most part, it's going to be very fast. There is a natural decline as our latency increases. And this is to be expected because as we go further and further away from the hosts, they have a longer distance that they have to communicate to each other. So that feedback loop that they establish, this series of I'm going to send you data and you're going to send me acknowledgments that you've received the data, it's longer and longer. And as we get to the end of this, as we sort of get to the very, very tip out here, we may not be getting 10 gig. We still may be getting upwards of 8 or 9 though, and this is fine. We're not experiencing any loss events, but our latency is getting very, very long, and we're still doing pretty well. The situations that we want to adapt from and sort of deal with are really here in these other use cases here. And this is a situation where we start to experience packet loss. And it's a very, very small amount of packet loss here. You'll note that it's 0.0046%, which really comes down to about 1 out of every 22,000 packets that may be crossing the 10 gigabit interfaces on an end-to-end basis here. When we start to experience this packet loss within a data center or within a metro network here, anywhere between sort of the 0 to 5 millisecond range, let's say, we can recover from that packet loss very fast because there isn't much distance between the two ends. They're able to communicate fast, they're able to determine that they've lost some data, and they're able to compensate for it. We still may be getting 7 or so gigabits per second. We may be getting 5 or so gigabits per second. And to most users, that's fine. They may not notice that that's a problem. As we go further away, as we crest the threshold of our regional network, and as we're trying to transfer on a national or a continental or an international basis here, this is where it starts to fall apart. Even that small little minute amount of packet loss is going to cause us to experience speeds that are below a gigabit per second. In some cases, hundreds of megabits, maybe even kilobits. And we're unable to really deal with the scope of this because of the latency that is increasing and the fact that the hosts are not able to communicate very quickly that they may have dropped a packet somewhere along the path. And this is experienced by all users, and the frustrating portion for this is that they don't understand what's going on here. They may be able to assure that their own local network is working fine, but they don't really have any insight into if this is a packet that's being dropped at a regional level or a national level or a continental level. And this is the rub on why we need to have proper measurement and monitoring in place so that we can detect this before it happens and hopefully get out there and fix any problems that may be occurring, as well as be able to educate our users and say, hey, the reason that you're experiencing this issue is because of this, and then work with them to try to sort out if this is an application layer problem or a network layer problem or vice versa, whatever the case may be. So I typically do a live demo, but because this is a webinar, I don't want to take the risk here, but hopefully sometime in the near future we can do a video about this and do the live demo. How do we accommodate TCP? As we've seen from that previous example and talking through the graph here, we need to have sufficient bandwidth to avoid congestion. That's the first step. But the second step is making sure that the equipment that's in the path has deep enough buffers in the routers and switches, everything is tuned properly, and that we do have measurement and monitoring in place so that we can figure out if something does go wrong. Things have a tendency to break. Hardware doesn't work forever. Bugs may be introduced into the software environment. All of these things are possibilities. And having persona in place, and as we'll see from some of the examples later on today, really helps to figure out when these things are going to be going wrong. So let's get into some of the Science DMZ design patterns here, which will help motivate a little bit about why the networks are designed this way. Data mobility and performance requirements for data-intensive science are much different than what we would use to design an enterprise network. In an enterprise world, default configurations are usually okay. We have the concept of a converged network architecture that is trying to protect against many different things that may be occurring at any given time. We have our conventional security tools and policies like firewalls and intrusion protection systems that may stomp down on network traffic unknowingly to try to protect the environment from the bad stuff that may be occurring. And all of these are fine. We also may be using legacy data transfer tools, and we may just have a model where we're not proactively trying to look and find if there's a network performance problem that may be out there. All of this works well for a commodity network, but when we're dealing with these high performance tools, we need to make sure that things are a little bit better. We need to use a more performance-based approach as we're doing this. Dedicated infrastructure for wide area data transfer, well-configured hosts, capable network devices, and we need to have that proactive operational model that allows us to figure out when something is going to be going wrong. We also need to make sure that our security posture is well matched to that of these high performance science applications. Trying to send a big flow through a monolithic firewall that is inspecting traffic will inevitably slow down that flow and cause problems just the same as if we were dealing with congestion or some other physical deformity of the network. So the Science DMZ itself takes on a bunch of different forms. And what we're going to do now is we're going to show a couple of just very brief examples of what this may look like. There's a couple of themes that are going to come at it in this. First and foremost, trying to eliminate the sources of packet loss and packet friction as best as we possibly can. And then from there, trying to address the use cases of what the science complex needs to be productive. So the first example is more of a bad example. This is what usually happens in a situation where somebody invests in trying to get a high performance data transfer node and just install it into an existing network without thinking about this very critically, without thinking about this in terms of, is this a very valid use case to be using on my network as is? And what does this look like? If we look at the bottom left-hand corner here, we have our high-performance data transfer node. It probably has a high-performance application like Grid FTP or FTT or something running on it. And we just plug it into whatever network we have available. This is often something in an office building or a classroom environment, and it may be a 10/100 drop, maybe it's a gigabit per second. We really don't know, but it's most likely just a converged piece of the existing enterprise network. And this has to be drugged through our campus environment. It has to go through perimeter firewalls before it finally hits to the outside world here. One of two situations is going to happen with this device. Let's do the push situation first. Let's say that we do have data that lives on this node and we want to send it out to a supercomputing center somewhere. This is going to burst, and it's going to attempt to burst at whatever line speed it happens to be connected at. If this is connected at 10 gig or if it's connected at 1 gig, it's going to buffer up all the data that it needs to send, probably several gig, maybe even a terabit, and it's going to try to push it out. And because a network card is a binary creature, if it has data to send, it's sending it at that rate. We now have a glut of data that's going to land right here onto this first hop device. Now, what happens? If we had a big burst of 10 gig or 1 gig per second data that's coming in, if there isn't enough buffering right here, it's going to be dropped at this first hop. So most likely some data may get through. It'll get passed through the site or campus LAN, and some data may get through here as well, depending on how busy all of this other stuff happens to be. We may get a little bit of a pruning here as well if there isn't enough storage, or if this device happens to be very busy. If we started with a 10 gig flow, we're certainly not going to end with a 10 gig flow by the time we even get to our site border router, and then we're off onto the outside world. So even before we get to the outside world, our performance is taking a significant hit because of this. We can think about this occurring in the exact same way, just in the opposite direction, except the first device that may be pruning us may be this perimeter firewall. It's trying to do deep packet inspection. It's trying to figure out what's going on with this flow, and it may be dropping the packets right here instead. What this all leads to is that even though this is a high performance node, it's well tuned, it has a high level of performance from the application itself, the environment that it is placed in will mitigate anything that it's trying to do. So we will not have high performance in this use case. And that's frustrating for a user. They spent all this money and time and effort trying to hook up this device here, but because there isn't an environment that's built for success, things aren't going to work very well. So a better approach that we have in this situation here is dealing with Science DMZ design. And this is the most basic Science DMZ design, and it's very cartoon-like, and I'll walk through the different pieces of this. Not everybody's network looks like this, but this is the simplest and probably the easiest way that an existing site can experiment with something like this. So using some of the design principles that we talked about earlier, you'll notice that this isn't based back here in our site or campus LAN. In fact, it's at the border device right here, as close to the border as we possibly can make it. And we carve off this little enclave right here. We have a dedicated Science DMZ switcher router right here. It is not just exposed out to the world, you'll notice. We do have per service security policy control points. And what does that really mean? That doesn't mean it's a firewall. That means that we've installed some ACLs. We know the applications that are running on the persona node. We know the applications that are running on the DTN. We put in some high-level ACLs here that allow those ports to communicate to the outside world. Now we have our clean high bandwidth path that's been established. So in that previous situation where we had a data transfer that needed to occur here and pushed out to some computing center, or vice versa, some instrument was sending us information this way, now we don't have to contend with all the site and campus LAN protections and older infrastructure. We have two hops. We have to deal with our Science DMZ hop right here. We have to deal with our border hop before we're able to hit the wide area side. By removing all of those different pieces of the path, it greatly simplifies and sets up this transfer for a little bit more success than we would experience otherwise. The same can be said for persona. Any network traffic that needs to bounce to the outside world will be able to bounce here and out and ensure that we have pretty good performance. And this should be our canary in the coal mine. It'll tell us how well these data transfers are going to be able to do. If we need to access things within our site, we still can. We can initiate a transfer from this data transfer node into the site or campus LAN over here. And because it's such a short RTT, we're talking probably 1 to 5 milliseconds between here and here. Even if we do experience packet loss from this or any of the stuff that may be here, we're still going to be able to guarantee a pretty fast recovery. We'll be able to see that there is events that are happening, but for the most part, we should have a pretty good performance characteristic, even though we are experiencing some packet loss there. So this is the most basic design here. What does this look like if we were to step up a little bit and go to the next level here? Let's say that we're trying to run a high performance computing center or some other large facility that has a lot of things that are going on. Let's say that we need to have several DTNs that are backed up to a parallel file system. Well, the DTNs don't necessarily need to have all the data living on them if that's the case. They have 2 feet. 1 foot sort of sticks into the file system and is facing the users. 1 foot is facing the outside world so that it can move the data. These act like capacitors now. So instead of the data having to be staged to these directly, it can live here in the parallel file system and it can be pushed out to the outside world, or vice versa. The outside world can push the data to these, and then the data will just show up where it needs to, where the supercomputer can use it, where other users have the ability to tap into that and use that. You'll notice that we still haven't exposed all of this stuff to the outside world. For the most part, this is a data-centric architecture because the data must still flow into that parallel file system via these data transfer nodes. How do we enforce that? Well, first and foremost, even the supercomputer probably has a front-end switch that needs to be logged into. Remove the data transfer tools from that. We don't want people trying to use SCP or something like that. So for the most part, if you want to get data in or out, it has to go through these DTNs. Could you still have a little firewall here in front of the supercomputer? Sure. If you need to protect against that sort of stuff, absolutely. If you want to have a jump host or a bastion host or something like that to enforce logins, that's fine too. For the most part, you can make this as secure as you want to, as long as you ensure that the data path, the path from these data transfer nodes to the inside and to the outside, is not being impeded in any way. So a couple of last thoughts here. We've shown a couple of architectural diagrams, but what about the individual pieces here? The requirements for the gear that lives in here is a little bit different. We don't need to have the most fully featured routers and switches in this path. In fact, the Science DMZ devices only need to be able to do a couple of things, but they do need to be able to do those things very, very well. And what that means is that they need to be able to have a very fast single flow go through them. We need to be able to measure and validate what's going on. And typically this means that you can't go out and buy the most inexpensive device. You know, you need to make sure that this is going to be a performant machine that can do well. And what are we trying to optimize for? We're trying to optimize for use cases like this. And what that typically means is that those data transfer nodes that I talked about and alluded to, they're going to be speaking in bursts. Whenever there is a large amount of data that needs to be sent to the outside world, it's going to have to go through that data transfer node and by extension, the switches that are in its path. So if there is a big burst that's going to come down here and consume memory all of a sudden, that's memory that will not be able to be available to other stuff that happens to be coming in if there happens to be background traffic. And this friction within the device is often where packet loss is going to occur. That internal congestion may be what causes us to have to back off our DTN traffic, which reduces our performance. Where could this happen? It happens in a couple of places around our campus. Whenever we're going to have a speed step down, let's say that we happen to have a 10 gig path, but then we happen to have a 1 gig step down right here. If there's 10 gig of traffic coming in and it needs to be squeezed in to fit a single 1 gig, there's going to be packet loss that occurs right here. Equally, if we happen to have a lot of busy stuff that's going on right here, as well as a data transfer node competing for resources here, we may start to experience the packet losses there. So a lot of what ends up happening with the design of a network like this is that you are engineering for the bottlenecks and trying to figure out where they are and try to remove them so that they don't impact things. Things that we think are important here is that deep interface queues really do matter. And you have to be careful with this because often you're going to run into situations where the marketing language of the device that you're going to be buying doesn't give you exactly what you're looking for. What matters here is what TCP sees. And if TCP isn't able to acquire enough memory and buffering within the device, that's where your performance is going to degrade. We also need to make sure that we have good counters, because if we can't reliably count every single packet that's going to be coming in with this specific flow, we can't tell if we've dropped any, thus we can't figure out if this is really the thing that's causing us problems here. The way that we like to codify this is that if you can't get single flow line rate speed from two devices that are connected back to back, that's probably not a good device that you should have in your network. You know, and as latency increases, as we've seen from those examples, it's only going to get harder and harder. So always try to verify this as best as you possibly can. Under-buffered devices are really the single greatest threat here. And what does this mean? This means that those little tiny top-of-rack switches that are often used just to connect up a bunch of things that may be living within a rack before it jumps out of the rack and out to the greater world, those are not going to be something that you want to have in your path at all. They're inexpensive, they don't have a lot of memory within them, and because of this, this is the thing that we often find limits high-performance flows more than anything else. Non-passive stateful security devices are pretty much the same. They do not have a lot of buffering, and they have to do a lot of processing to do their security job. And then anytime you're jumping around the OSI stack, you're adding friction. E.g., you know, if you're trying to do routing and you don't need to, you can get away with doing switching or something like that. All of these things contribute to a lot of the performance at the end of the day. So a really quick block diagram to explain what I'm on about here. If you look on the inside of a switch, it typically looks like this, where you're going to have a bunch of input lines, you're going to have a bunch of output lines. There's a routing function and a fabric that sits in the middle here, but for the most part, you are gated by these little features right here, which is how much buffering you can accept on your inbound and on your outbound. Data is going to be arriving from multiple sources at any given time. You do have this finite amount of memory. It may be per interface, like as we see in this picture right here. It may be shared. And that's one of the dangers that we have to run into, is we have to understand what the inside looks like. Because if we don't, and we're dealing with a shared memory environment, that's where you can run into situations where one big flow coming in from your DTN is going to consume everything, and it's going to block out the other traffic, or equally, the other traffic will prevent and starve out the DTN from being able to get something in there. What ends up happening here is that the processing engine extracts the packets and pulls off the header information and figures out where things need to go before sticking them onto the output buffers. So that's the basics of the inside of a switch right here. One piece of math that's good to remember, and this will help guide you as you try to pick out how big of a switch you need to do to support your different deployment situations here, is called the bandwidth delay product. So let's do a really quick math example here. Let's say you have an expectation of being able to do that 10 gigabit per second cross-country flow like I had in my graph earlier on. For sake of argument and to make the math easy, it's a 100 millisecond flow. If we convert the bits to bytes and we convert the milliseconds to seconds and all those different things, we basically end up requiring that we need to have 125 megabytes of memory available within that device to accommodate this. And it's not just that first hop device, it's every device. If you ever come across something in the path that is limiting that performance footprint, you will not be able to achieve this 10 gigabit per second expectation. And this is why we term these things the bottleneck, because whatever memory is available, you will be condensed down to that memory footprint and that capacity and that speed, and you won't be able to exceed that no matter what you try. So engineering your network to be able to accept and deal with these requirements is the best possible thing that you can do for these science requirements here. So let's do the converse of this. Is buffering isn't important on the local area network. And this is why those top of rack and smaller cut through switches that you often see in the data center environment don't have a lot of memory in them, because they don't need it. If we're dealing with a 1 millisecond or a 2 millisecond latency and you want to be able to do that same 10 gig performance, you don't need 125 megabytes, you need 1.25 megabytes. And because of that, those smaller switches are going to be implemented in such a way that they don't have that available to them. Buffering matters for the WAN, and that's why a lot of the design characteristics that we saw were trying to place the wide area transfers away from all the stuff that we have within our campus and as close to the border as we possibly can. That way, we only need to over-engineer the DTN path to the outside versus trying to over-engineer everything else within the campus environment. It'll be a cost savings in the long run, and it will facilitate those wide area transfers without having to upgrade everything else. So what does this look like in practice? If we take a look at the results of a performance test, in this case it's an iPerf test, when we run out of buffering, TCP performs in a very, very specific way. We're ramping up and we're doing well. We're at about 148, 160 megabits per second, and then we take this sudden hit of loss. And that is because we've ran out of buffering. In this case, we exceeded about 5.36 megabytes and we ran out. TCP reacted poorly. It said, please back off. I don't have enough space to deal with this. Because it backed off, the performance degraded a little bit, as you can see right afterwards. It ramped up and it got a little bit better over time, but then we took another hit again. In this case, we were consuming about 16 or so megabytes per second, and then we experienced another loss event. So this example goes to show that it is a fluid thing. Memory in the network is going to depend on congestion. It's going to be depending on use cases. And the protocols are designed to back themselves off. As long as there is enough capability in the network, though, things are guaranteed to work at a high rate. So I think I'm over my time here. I'm going to skip a couple of the next little slides here and just sort of go to the end. These slides will be posted for people who who would like to see them at the end. The couple of takeaways that I'll sort of say here is that the Science DMZ design is adaptable. You can do whatever really works well for your use case and for your scientific use case. Before you go out and buy something, request a demo unit or two. Try to learn about how these things behave and how they're going to be working. And try to develop worst case scenarios. In this case, you'll learn a little bit about how PerfSonar is able to give some of these pieces of feedback about how a network is working. Learn about how cross traffic is going to be impacting some of your environmental considerations, your switches and your routers, and what it looks like to test the things that are far away. If you can't get that single stream of TCP to work, buffers are often going to be the core of the problem. And it really is worth spending that amount of money on that. That's going to be the way to sort of get your success factors up with this. Designing it such that the DTN has a clean path to the outside world is the best way to start. So that was it for this first set of slides. I am going to stop my share here so that I can see the screen again. And I haven't been following any questions, so I'll just wait and see if any of my panelists have any questions for me.
Jason, I have one question.
Okay.
So based on your experience at EPOC, what are the most common type of assistant requests that you receive regarding Science DMZ high-speed networks? What are the most common issues that you see?
I think there's probably two categories. The first category is just how do I get started? People asking questions about, what's the best way to integrate this in? What are the devices that I should be considering? How can I sort of optimize given I have limited budget and certain use cases? And to that, the answer is almost always, know your network, go and talk to your users. You're able to impact a great community by starting small. You don't have to go out and upgrade every single device on the network. And I think that that's one of the common misconceptions is that people think that they need to build 40 gig or 100 gig to desktop computers. And that's really not the right way to go about this problem. It's about identifying one or two, maybe more use cases, trying to build the network around those. Moving the DTN close to the border, still having your security in place, but having those have that clean shot out to the outside world. And then from there, integrating that into the scientific workflows and figuring out the different pieces that need to be supported. And I think the other question that we often run into is once people build something and it's not working the way that they thought it should, it's how do we do the testing? How do we figure out what's going on here? And often the answer is, well, let's get some PerfSonar verification in place. Let's take a look at how things are working in a live fire environment, doing some live monitoring, figuring out if there's loss locally or regionally or nationally, and then backing up and trying to figure out where the problems may exist.
Thank you. There is another question. Mr. William, in a network instrument such as public education that are challenged by human power and budget that require third-party vendors to resolve network control issues and still remain security and performance, how do you handle third-party vendors? How do you handle third-party content filtering?
So if I understand correctly, third-party vendors is probably just the reseller market that's attempting to come in and install things to help you to your benefit. If I have that wrong, Mr. Williams, please correct me. The way that EPOC at least works is that we are funded by the NSF, and because of that, we work for all of you. If you ever want us to be present on a phone call or give a quick little QA with your team or anything along those lines, please reach out. We are basically sitting by the phone waiting for people to ask us these questions. And we've brokered conversations before between people, and mostly it's just to make sure everybody has a common understanding of what the outcomes need to be. Often it is the case that the vendor community doesn't quite understand what the scientific community needs. You know, they want to make sure that they have full availability and things like that, and that's just not a metric that we're really looking for here. So often, if we could broker those conversations and be the person who sort of translates the scientific use case into what the network requirement really is, that's usually be the way that we try to get that going. So I think I didn't flash it up there on the screen, but our email address is just EPOC, EPIC, EPOC at iu.edu. Send us a note, and we're happy to work on that.
So there are several other questions, but I think we can take one more. We're a little bit behind schedule, and then we will.
Sure. And I can type the answers to the other ones while the next speaker is going. So pick whichever one you'd like me to do live.
Okay. So the last one, and then we will switch, by the way. We have Neil Carwell from Google. If you can promote him, Jason, so he can share a screen. But the last question is, can you talk about the potential congestion on the path between the border router and the WAN? How would you recommend protecting the enterprise traffic from the Science DMZ traffic on that link?
Okay. Let's see. Which question was this, Jorge? I want to read it again.
Yes, it's Brandon Payton.
Oh, Brandon. Okay. Can you talk about the potential congestion on the path between the border router and the WAN? How would you recommend protecting the enterprise traffic from the Science DMZ traffic? Okay. So I guess to do that, let me bring up the picture again. All right, so let me share this so that people know what I'm talking about. So I believe the question was, how do we protect this stuff over here from this stuff over here? You can still think of there being sort of an invisible wall that protects the Science DMZ and the enterprise from each other. In fact, one of the mistakes that people often think is that they need to sort of put a back door in place between this DTN and this site over here. There really isn't any danger. In fact, I'd say it's encouraged that if you want to run local traffic through the border device and through the firewall into the site or campus here to get to your DTN. In fact, that's usually encouraged. And the reason that you want to do this is because think of this as the Wild West over here. You don't really know what's going on, right? You have all kinds of BYOD and just odd traffic profiles. And that's the reason why you have a border firewall, right? The border firewall is to protect against the unknown. Over here, it's known. Everything that originates from or terminates in this environment, you should have an understanding of. This is only populated with applications that are doing data transfer. That's all they're doing. It could be Grid FTP, it could be Globus Online, it could be FTT, it could be SCP. Whatever it is, you know what the application profile of this is going to be. You know what the application profile of this is going to be as well. Under no circumstances should there be email, web, video, anything in this environment, and that's because you're maintaining a clean room, so to speak. You know, you're allowing only the things you like in and only the things that you like out. So if you need the data transfer from something over here, you know, you're going to want to use the tool that's on this device to initiate that data transfer in and out. And in terms of sort of the sharing of this infrastructure, right, the only spot where these things really touch is right here on this border device. You could maintain a separate BGP peering here if you really wanted to, and only have research traffic come in and out, and only allow commodity traffic to go in this way. Some people go as far as to treat this as its own separate sort of BGP peer and have it peer with the campus. You know, there's a bunch of different ways you can try to do that to segregate this stuff out. But at the end of the day, you want to maintain the ability of this to be protected against the knowns. And when we get into the BGP session and stuff tomorrow, I think Hans and Eli Dart will be able to explain that a little bit more. So hopefully that answers the question for right now. I'll type in a little bit more substantial answer in the chat and give a link or two that may be helpful as well for Brandon.
Thank you, Jason. Um,